All right, we're going to start in chapter 4 here. We're going to do sections 4.1 and 4.2 in this video. So we talked about covalent bonding a little bit when we talked about bonding in general, but we're going to dive in this chapter to covalent bonding. So covalent bonding, remember, results from the sharing of electrons between atoms. And so let's say that this hydrogen has one atom and this hydrogen has one atom, but they both want to get to look like helium, which is the nearest noble gas. When helium has two valence. And so they're going to want to share until they get two. If they both put in each one into a bond, then they can have access to both of these. So we call this a bond. Each bond is going to have two electrons that are being shared. And a molecule is a group of atoms that are held together by these covalent bonds. Unshared electrons are called non-bonded electron pairs or lone pairs. You'll hear me use the term lone pairs more than unbonded electron pairs, but that's what it means. So for example, let's say we have hydrogen and fluorine that want to bond together. Well, fluorine just needs one more to get to 8, and hydrogen just needs one more to get to 2. So there's no need for them to share more than one of these electrons. So this electron will get shared and this electron will get shared. So here are the shared ones. We draw a line to indicate the shared electrons. This is pretty important for moving forward here. A line for shared electrons. Now, some of you may have learned in the past that this is fine. I mean, technically it is correct, but it is a lot harder to see which of the dots are shared and which are only on fluorine if we do it this way. If we use a line for the shared ones, anytime we see dots, those are not shared. So fluorine is only sharing with these two electrons in this line, and it's not sharing the rest of its 6 electrons here. So each line represents 2. Line equals 2 electrons that are shared. And so when we're thinking about counting electrons in a minute for Lewis structures, each time you see a line, you're going to count that as 2 total. But when you're counting for how many does fluorine have at its valence, fluorine will have 1, 2, 3, 4, 5, 6, but then it has access to both of the electrons in the bond. So that gives it 2, 4, 6, 8, which is the special number, that octet rule that I mentioned, and now fluorine is happy. Hydrogen has access to 2 in the bond. So hydrogen is happy because 2 makes it look like helium, and who's a noble gas. So they do the sharing to get to the noble gas, right? We talked about the octet, so fluorine has got an octet or 8, and then hydrogen is getting 2, and the hydrogen is an exception to the octet rule. It only wants 2. It's cool with that. Lewis structures are electron dot structures, but for molecules. And so we show the location of all those valence electrons. So remember when we did electron dots, we would put dots for the valence around the symbols. Well, Lewis structures are kind of like that, but we are going to show all the valence electrons from all of the atoms in the molecule, and we're going to show how they're being shared. So here are some examples of Lewis structures. Again, I don't really want you drawing your Lewis structures in this way. You may have learned it in this way before, where you kind of draw the dots and you kind of connect the dots and smush the dots together. However, it is really difficult for me to be clear in what you understand about who is shared and who is not shared at this level. So I'm going to ask that you use the lines to represent the shared and the dots to represent the unshared. And that's just going to make it a lot clearer and cleaner for everyone to see. You really don't see chemists using this method of drawing Lewis structures often because it is confusing. We use lines to represent shared. So one line equals 2 shared electrons. So if we were to have multiple lines or something in between, that means we're just sharing more than 2. And so these are just some examples of some Lewis structures. We're going to walk you through the steps to drawing Lewis structures in just a minute. So covalent bonds are between two nonmetals, or if you have a metalloid and a nonmetal. Um, that's because when we have ionic stuff, one is willing to give and when one takes. With covalent, they all want to take. They all have high numbers of valence electrons. They don't want to lose electrons. So if everybody wants to take electrons and nobody wants to lose them, we have to share them. How many bonds will form? Hydrogen forms one bond, only ever one. And then atoms usually with 1, 2, or 3 valence electrons form 1, 2, or 3 bonds. Atoms with 4 or more valence electrons form enough bonds to give an octet. So you can figure out how many bonds. This is going to be predicted typical. We just use this word typical number of bonds. It's not always exactly the same. But if we have 6 valence, for example, for oxygen, it's usually going to make 2 bonds. If we have 7 valence electrons, like for fluorine, it will make 1 bond. If you look at the periodic table, you can kind of see I like this visual better. Hydrogen makes 1 bond, 0 lone pairs. Carbon likes to have 4 bonds, 4 lines, and 0 lone pairs, no dots on it. Nitrogen likes to have 3 bonds and 1 lone pair. Oxygen likes to have 2 and 2, and a halogen, like fluorine, chlorine, bromine, likes to have 1 bond and 3 lone pairs. So see how it kind of goes 4, 3, 2, 1, 0, 1, 2, 3? You can see this pattern. So nitrogen is going to be kind of the leader of that group. And so nitrogen and phosphorus are going to behave similarly. Oxygen and sulfur are going to behave similarly. Halogens behave similarly all the way down. Carbon and silicon behave similarly. So all the nonmetals basically under that group are going to bond like this. And that way you can kind of just get a general idea of this is, again, this is going to be, I'll say typical here. Can it go different than this? Absolutely. You can have a carbon with 3 bonds and a lone pair, and that happens in carbon monoxide. You can have nitrogen with 4 bonds. That happens in ammonium. You can have oxygen with 1 bond, right? That happens. These are typical bonding patterns that'll get you through most of the work we do in this class. However, don't keep a closed mind, keep an open mind, and basically, as long as they wind up with 8 valence electrons around them, it can be whatever kind of bonding pattern, but these are the typical ones, and it's helpful to know the typical ones as you start out because you can get a feel for does that structure look correct or not, essentially. Covalent compounds are everywhere. There's a lot of covalent compounds in the chemistry of the heart. So glycine is here. It's just showing the hydrogens are the little white ones, carbons are the black ones, nitrogen is blue, and oxygen is red. So glycine, nitroglycerin, and then water is really important. So these are just some structures, ball and stick models. We're going to be drawing Lewis structures to kind of mimic that. A Lewis structure shows the number of all of the atoms in the compound, what the identity of those atoms are, and how they're connected. A molecular formula gives me how many, but really not how they're bonded. So molecular formula is what we already have. So example molecular formula would be like H2O. An example Lewis structure would be showing me how everything is connected and what my electrons are doing. So this is the difference in these two things. So to draw a Lewis structure, so general ground rules, we're only going to draw valence electrons. We're not going to worry about total electrons. We're only going to count valence. Every main group is going to have 8. There are some exceptions we'll talk about, hydrogen being one of them. Hydrogen gets 2. So everybody wants to make sure they have 8. That's the octet rule, but hydrogen is going to get 2. We'll talk about some more exceptions a little bit later. So the first thing we're going to do, and I'll show the examples, is to arrange so that you think they're bonded properly. Now, how do you know if they're bonded properly? Well, if we know that hydrogen can only make 1 bond, we can't really put hydrogen in the middle. Because if hydrogen's in the middle, now it has 2 bonds. So think about just how we're going to arrange things. For example, this is CH4. If you think about the common or typical bonding patterns, it will be a little bit helpful because you know carbon likes to have 4 things around it. So if you have carbon and 4 things, Then we can put carbon in the center and those 4 things around it. And then this step 1 and step 2, I think I switched them in the notes I'll show you in class, but it doesn't matter what order we do these in. And so we can use those common bonding patterns. So for example, if we have CH5N, if we have a choice, we can put 4 things around the C and 3 things around the N, or we can put 3 things around the C and 4 things around the N. Well, we know from the typical bonding pattern that carbon likes to have 4 things around it, or 4 bonds around it, and nitrogen likes to have 3. So we'd use this one, not this one, if that makes sense. So nitrogen doesn't like to have 4 lines. Carbon does like to have 4 lines. So once we get that typical bonding pattern down, it'll be easier for you to figure out where to place things. Next, you're going to count up all your valence electrons. So you're going to count up all the electrons that are brought to the table. Carbon has 4 valence. There's 1 carbon with 4 valence, so it brings 4 to the table. There are 3 hydrogens. Each hydrogen has 1 valence, so it brings 3 to the table. There's 1 chlorine. 1 chlorine has 7 valence. It brings 7 to the table. So total in this structure, we have 14. We don't need to worry about the fact that carbon started with 4, that hydrogen started with 1, that chlorine started with 7. We're going to throw that out the window, and we're going to take these 14 and divvy them up however we want to give everybody their octet or their 8. So once we arranged all of our electrons, we're going to put 1 bond between every 2 atoms. For all your main groups, you cannot give more than 8. We'll talk about exceptions to the octet rule, but we're going to stop at 8. And then for hydrogen, we're going to stop at 2. And then we're going to use remaining electrons to give everybody their 8 using lone pairs, beginning with atoms on the outside. So we're going to start with the outside and work our way in. So here with CH3Cl, we put the C in the middle. We bonded it with 4 bonds to the 3 H's and to the Cl. Now, if we count up the electrons we have in the bond, 2, 4, 6, 8, right? We had 8 left. So, or sorry, 6 left. So we can put them on the chlorine. We need to have 14 total in the structure. So if we count 2, 4, 6, 8, 10, 12, 14. That's total. Let's make sure everybody has their octet. Each oxygen can only have 2. So, sorry, each hydrogen can only have 2. So a line here means 2, so that hydrogen is good. A line here means 2, that hydrogen is good. A line here means 2, that hydrogen is good. Let's check our carbon. Carbon has 2, 4, 6, 8. And we're counting these 2 for hydrogen and these 2 for carbon because they're sharing them. So the carbon has 2, 4, 6, 8, and so it means it's happy. Then what I did was I gave these dots to chlorine because we can't keep bonding because I can't put more than 8 on my carbon. So I have to do my carbon with 8 max, and then that means that chlorine only had 2 here. I need to give it more to give it 8, so I need to give it 6 more. We're going to give in lone pairs. We're going to give pairs, not in singles. And so once we have to count our chlorine, we have 2, 4, 6, 8. So that means that it's happy. You're going to get a lot of practice with this. So, you know, and I'll give you some additional kind of written out steps in class. But, you know, just practice and play around with it. I would do this with a pencil for sure. You're going to erase and mess up and, you know, it'll probably feel weird before you get better at it. If the valence electrons are used and your center atom still doesn't have enough, let's say that our carbon didn't have enough, we would have to make more bonds to the carbon by removing some from the chlorine. So let's see what that looks like. Let me just kind of back up for this one. So with oxygen here, if we start with 2 oxygens, we have 12 valence electrons because each oxygen has 6. If I kind of just put the bonds here, and let's just give out the lone pairs. So the order that I'll show you in class is to give out your lone pairs first. And I just focus on one atom at a time until they have 8. So 2, 4, 6, 8. And I have 12 electrons to give, 10, 12. So I give out in pairs, and I'm just giving out my dots after I have my single bond. Next, I need to check to see, does everybody have 8? So this oxygen on the left here has 2, 4, 6, 8. So this oxygen is good. However, this oxygen has 2, 4, 6. It's not good. So if one of them is not good, we have to share more. So we have to kind of rearrange this. So we're going to erase a pair from our O on the left and replace it with a double bond. Now you may say, why don't we just take away this pair and put them over here? Well, if we do that, then we just changed who's happy and who's unhappy. The goal is to make everyone happy. And so we are going to erase a pair and replace it with another bond. So I took electrons from here and I made them into this bond. If that makes sense. That would be a double bond. And so there's 4 electrons when I'm counting. So 2, 4, 6, 8 for the left oxygen, 2, 4, 6, 8 for the right oxygen. Everyone's now happy, and that works. Triple bonds look like this. We would count for 3 different bonds. So this nitrogen on the left has 2, 4, 6, 8, and the nitrogen on the right has 2, 4, 6, 8. Play around with it. I'll show you a list of steps. If you look through the slides for the in-class stuff, I'll show you like a list of written out steps that maybe makes a little more sense. And you'll know you just have to go through there. There's some practice here in these slides. So look through the slides and try the practice. So I would stop and pause the video, try this out, and then unpause and work through it. And so this is just kind of taking you through the arrangement, the valence electron counting, and then they added in all their bonds, single bonds to everybody, always single bond first, and then they added the pair of dots. They could have put the dots on this carbon, but they chose to put them on this one, doesn't matter. If we count the octet, 2, 4, 6, 8, the left carbon is, or the right carbon is good, but the left carbon only has 6. So what do we have to do? We have to take this carbon, has these extra. It can't be stingy, it's got to share with its brother. So you got to take these 2 and make them into another bond. So you'll take these 2 and make them into a bond, right? So each carbon now has 8. This carbon has 2, 4, 6, 8, and then the right carbon has 2, 4, 6, 8. You'll get used to this, I promise.